Given to us is what the coefficient of friction is between the surface and the crate is 0.25. And the mass of the crate, 50 kilograms. So we want the minimum value of P to stop the crate from moving down the incline. We're not given any of the dimensions of the crate, its length or its height, in which case, since we don't know that information, we can treat it just like a particle. When we're treating something like a particle, we can study the slipping. We can't do anything about tipping for this problem, but we'll get to that next time. So our free body diagram, I'm going to isolate the crate from the surface. So I'll have that construction line. So the surface is 30 degrees. So isolating the crate, what forces are acting on the crate in the free body diagram? Yeah.
Your force P.
Right, so we're applying that force P, which we are to solve.
Force up from the surface.
Right, so the normal force, so that'll be the force between the surface and the crate, which is always perpendicular to the surface. So I'm going to call that, I should call that lowercase n, so that we don't confuse it with newtons later on. So this is going to be 30 degrees from the vertical or 60 degrees from the horizontal, since again it's perpendicular to the surface. The weight of the crate, which will be it'll be towards the center of the earth, so that will be in the negative y direction. So mg, right, we know the mass, so the weight will be 50 times 9.81. So the weight or the effect of gravity, 491 newtons. All right, now let's come to the friction, since that's going to be the trickiest part of this. So what direction should the friction be pointing? Yeah.
Up the hill.
Right, so up the hill. So two things about it. It's parallel to the hill. It's always parallel to the surfaces that are interacting, in which case it's the crate and the surface of the plane. And we know, so it could be down or up. We know in this case it's up the hill, because we're looking at a situation where the crate wants to move down the hill, and we're just pushing hard enough so that it's not. So in this circumstance, that force of friction is opposing that motion, so therefore it's up and to the right. We have all of our forces there, so now we, again, assume it's in equilibrium. So we're going to get, well, this is a particle for the purposes of this problem, because we don't know any of the lengths. So we can always sum forces in the x or the y. Or I'll choose x and y for this example. So in the x direction, I have all of the applied force P. I have Fr cosine 30 minus n sine 30. And in the y direction, I have all of my weights, 491 down, plus the force of friction times sine 30, plus the normal force times the cosine of 30. So I don't know P, I don't know Fr, I don't know N. Three unknowns, two equations. Again, I can only get two equilibrium equations out of my picture. There's not another object to draw, so it's not a frames and machines type of thing. So I need at least one more equation to be able to solve for my unknowns. So where do I get an additional equation from for this? Yeah. Right. Because we're analyzing the minimum force we can apply, what we can interpret that to mean is that this thing, if we pushed any less, is going to slide down the hill. So we want to push hard enough so that it's just on the verge of sliding down the hill. And that will mean that's the lightest we can push so that it is in static equilibrium. So because of that, we can set it equal to mu times n, which is going to be 0.25 times n. Again, this is because it's about to slide down the hill, that they're equal to each other. But in general, the force of friction is not in general equal to the normal mu times n. Between these three equations and three unknowns, we can solve our system. So in this case, the normal force is going to be 495 newtons. The force of friction is 124 newtons. And what we're looking for is the value of P, 140 newtons. So if we push with 140 newtons of force, it's in static equilibrium, but if we push just a little bit less than this, it would start to slide down the hill. In the second question, we're asked, what's the hardest we can push the crate before it starts to slide up the hill? So the givens are the same. So it's P max before crate moving up the incline. It's still in static equilibrium, but now we're pushing harder, and it's on the verge of sliding uphill. So how does our free body diagram change between the first way we did it and then this way? Right. It wants to now slide, or it's on the verge of sliding up the hill. It would want to slide up the hill if there were no friction. So friction opposes that impending motion. So we have to flip. It's still along the same axis, but now it's down and to the left. So coming over to the equations, what does that change? Well, it's now down and to the left, so this is going to be a minus FR cosine 30. In equation 2, it's a negative FR sine 30. However, in equation 3, this is still the case. The force of friction on the verge of slipping is still mu times n, so it's still equal to 0.25 n. And this is where the problem occurs if you were to have a negative value of friction. I just flipped it here, I flipped it here, however, it does not flip here. The reason that it works, like when we have the wrong assumption of the direction of a pin, saying it's right instead of left, it's fine because everywhere it appears, the sign would flip on it. However, in these type of equations, with the friction, it flipped in two places, but not the third place, which means that we're not only going to have a different sign for our answer, we get a different magnitude, potentially, for all of our answers. So that's why if you ever get a negative friction or a negative normal force, you have to redraw it and then rewrite the equations properly. With this set of three equations now, we get a different set of N, FR, and P. So in condition 2, where it's just about to slide up the hill, the normal force rises to 663 newtons. The maximum force of friction is 166. And most important, the value we have to push with is 475 newtons. We can interpret this as the range of force we can push with where the crate's not going anywhere. As long as we push harder than 140 newtons, but less than 475 newtons, the crate will remain in static equilibrium because the force of friction will always match what we're doing to prevent any of that motion from happening. Once we push less than 140 or greater than 475, the crate will move in the, here down the hill if it's too little force. Here it will start to slide up the hill if it's too much force.